NVIDIA's market cap briefly surpassed $3 trillion. Governments are restricting the export of specific semiconductors. Data centers are being built at a pace not seen since the early internet. All of it traces back to a single question. What kind of hardware does AI actually need? And why is it so different from what was already inside every computer? The answer involves a fundamental mismatch between the work AI does and the hardware that computers were originally designed to run. Understanding that mismatch explains not just the chip shortage and the NVIDIA story, but why AI looks the way it does and why it costs what it does. Let's start with the CPU, the central processing unit that runs the software on every laptop, phone, and server. A CPU is designed for versatility and sequential speed. It has a small number of extremely powerful cores. Modern desktop CPUs have between 8 and 32 of them, each capable of executing complex, branching logic very quickly. If you need to run a database query, process a file, or handle an HTTP request, the CPU is the right tool. These tasks involve lots of conditional branching, if this, then that, and the CPU's deep pipeline and branch prediction hardware are optimized exactly for this pattern. Training a neural network is almost nothing like this. What neural network training actually involves is a very large number of very simple calculations, multiplications and additions, performed on large blocks of numbers simultaneously. A single training step for a large model might involve trillions of multiply-add operations across billions of parameters. Very few of those operations depend on the result of another operation happening at the same time. They're independent, they can run in parallel. This is the core mismatch. The CPU, with its handful of powerful cores, is built for sequential, branching workloads. Neural network training is a massively parallel, mathematically simple workload. The CPU does it the hard way, using its few powerful cores to process things one batch at a time. Enter the GPU, the graphics processing unit. GPUs were originally designed for rendering video games, transforming millions of triangles, applying textures, calculating light and shadow across enormous numbers of pixels simultaneously. All of that is also massively parallel, mathematically simple arithmetic. The similarity to neural network math is not a coincidence. It's the reason GPUs became the dominant hardware for AI. A modern GPU has not dozens, but tens of thousands of cores. Each core is individually simpler and slower than a CPU core, but running in parallel, they can perform far more total arithmetic per second than any CPU for workloads where the work can be done simultaneously. An H100, NVIDIA's current flagship AI chip, has over 16,000 CUDA cores and can perform around 4,000 trillion floating point operations per second. This is why NVIDIA, which dominated gaming graphics for decades, found itself at the center of the AI revolution. The company had built the best parallel compute hardware in the world, and parallel compute turned out to be exactly what training neural networks needed. But there's more to the story than raw compute. Before we get to memory, it's worth pausing on what parallel actually means in practice. When a GPU trains a neural network, it doesn't process one weight at a time. It processes entire matrices, large rectangular grids of numbers, simultaneously. A single matrix multiplication might involve multiplying two grids that each contain millions of numbers, producing a third grid in a single operation. The entire computation happens in parallel across the GPU's thousands of cores. This is called a GEMM operation, general matrix multiply, and it is essentially the only thing neural networks do at scale. Every layer in a transformer model is a GMM. Every attention calculation is a GMM. The entire architecture of modern AI is, at the hardware level, matrix multiplication running as fast as possible on as many cores as possible. Moving data to and from memory is often the real bottleneck. A chip that can perform enormous amounts of arithmetic is useless if it spends most of its time waiting for the numbers it needs to arrive. Modern AI chips are designed with this in mind. High bandwidth memory sits as close to the compute units as physically possible, and the interconnect between chips on the same system is engineered for maximum throughput. This is why the H100 uses HBM3 memory, high bandwidth memory, stacked directly on the same package as the compute die, providing dramatically higher memory bandwidth than conventional DRAM. And it's why the NVLink interconnect between multiple GPUs in a single server allows them to share memory and communicate far faster than a standard network connection. NVIDIA doesn't have the market to itself anymore. Google has been building its own AI chips for nearly a decade. called TPUs, or tensor processing units. TPUs are designed specifically for the matrix multiplication operations that dominate neural network computation, with no concessions to general-purpose graphics workloads. They're built into Google's own data centers and power everything from Google Search to Gemini. Amazon has Trainium and Inferentia chips for training and inference, respectively, running in AWS. Microsoft is developing its own AI silicon. Apple's neural engine is embedded in every iPhone and runs on-device AI tasks without sending anything to the cloud. Meta has designed its own training chip as well. The motivation is the same for all of them. NVIDIA's chips are expensive, supply-constrained, and represent a strategic dependency no company wants to be locked into. When a single supplier controls the hardware your entire product runs on, that supplier has significant leverage over your costs, your roadmap, and your ability to scale. There's also an efficiency argument. A general-purpose GPU still makes compromises. It's designed to run many different kinds of workloads. A chip designed specifically for one company's specific model architecture can shed those compromises entirely, optimize every transistor for the exact operations being performed, and achieve better performance per watt for that specific task. Building your own silicon means controlling costs, optimizing for your specific workloads, and not competing with every other AI company for the same hardware. There's also an important distinction between training and inference. Training, the process of adjusting billions of weights over millions of examples, requires the most compute and is dominated by large GPU clusters. But once a model is trained, running it to answer a user's question is called inference. Inference is a different workload, lighter per request, but running continuously at enormous scale, they say. The economics are different and the hardware can be different too. Inference chips can be smaller, cheaper, and more power efficient than training hardware because they're running a fixed model rather than computing gradients and updating weights. This is why you'll increasingly see AI capabilities moving onto devices, phones, laptops, wearables, rather than staying entirely in data centers. The inference workload for many tasks is small enough that dedicated on-device hardware can handle it without a round trip to a cloud server. Faster, more private, and free from network latency. Here's the mental model worth keeping. AI needs parallel arithmetic at scale. CPUs weren't built for that. GPUs were, originally for games, then repurposed for something far more consequential. The chip shortage, the NVIDIA story, the data center build-out, the government export controls, all of it follows from that single architectural mismatch between the work AI does and the hardware the world already had. The industry is now building purpose-built hardware from scratch to match exactly what AI needs. That will make AI faster, cheaper, and more widely accessible. And it will keep reshaping which companies and countries hold the critical infrastructure of the AI era. If this kind of systems-level thinking about AI is what you want more of, subscribing is how you get the next one.